Yeah, it's a great pleasure to have this actual seminar this week. We have Yixuan visiting Boston in person. Yixuan has been a great friend of mine, and he just graduating from Caltech. He has been always on the frontier of things related to Navier-Stokes. Like whenever I hear some progress on Navier-Stokes, I always ask Yixuan, okay, like what's going on there and stuff. So yeah, I mean, he has as you can imagine, he has a very rushed trip that he needs to get to the airport within 3 hours. So I'm very glad that he could make here and share with us some of the progress of the numerical approach and data-driven approach to solve one of the very important problems, the singularity in Navier-Stokes equation. All right, Yixuan, the floor is yours.
Yeah, thanks a lot, Yuanqi, for the kind hospitality and invitation. And again, because a very intimate, small audience, I would like to be interactive, so feel free to interrupt at any time or any array during my talk, and I will, yeah. I'd love to hear what you think, and I'm happy to go in detail into any aspect of my work, but I'm just giving a holistic overview of mine. Yeah, some of the stuff I did with Navier-Stokes, the way Yuanqi put it, and as the title was promising, we're talking about a discovery and verification of this singular and challenging patterns in this nonlinear PDEs. Oh, how do I? Yeah. So here, just a quick graphics slide of with equation at stake. So we have this three-dimensional incompressible Navier-Stokes. There's a couple of velocity pressure formulation. It's of profound importance because it's the equation basically that monitor anything that flows. So here today we're taking, of course, a mathematical perspective. So because we know, unlike algebraic equations, these PDEs cannot be solved explicitly, especially for this nonlinear PDEs. So what are some of the fundamental or basic questions that could be asked for these PDEs? So basically, it's just existence and uniqueness of solutions. Do solutions exist? If so, are there only one solution? So this boils down to first the existence of strong solutions. That's one of the 7 Clay Prize or million prize problems in math. Whether there's going to develop singularity for Navier-Stokes, three-dimensional on the whole space, in the class of strong, smooth solutions. A related concept is concerning the uniqueness of weak solutions. So the connection can be seen as a continuation after singularity. So if we relax a bit, we allow the solution to have some singularity, but it's still a physical in the sense that it satisfies all the energy constraints, satisfies the equation weakly. And then by construction of a John array, such solutions are actually existing for all time. So it's a global, and it's oftentimes the de facto space that mathematicians are working. But in this case, do we know if it's unique? And actually, so it's been an open problem for more than 9 decades. And with my supervisor, Tom Hao, and our junior student, Chen Heiyan, we established the non-uniqueness rigorously. And I want to say Chang has been a driving force to this project. Yeah, it's a very amazing project, collaboration, and it's via computer-assisted proof. So also again, the mental picture is you start from nice smooth data, you have a uniqueness and existence of strong solution for some time. Then after singularity, you bifurcate into infinitely many number of non-unique or weak solutions. So I'll talk about a bit of that later. But let's go to the high level, a big picture of Navier-Stokes today. So what is singularity? What is a blowup? Unfortunately, I'll not be talking about a great film by Michelangelo Antonioni, which I highly recommend. But I hope my talk will also be marginally as entertaining and interesting. So here, if we zoom in to see what's going on, the precise statement, we have the incompressible Navier-Stokes. When there's no viscosity, that's the Euler equation. And when we talk about a blowup of certain quantity of interest, let's say the velocity u or the velocity a W, it basically means that our affinity norm tends to infinity as t tends to some finite time a t. And basically, just to reiterate, the Clay-Price problem asks if such a solution has singularity for a very nice data. So in particular, because the singularity can be very hard to find and compute, so something we're interested in, mathematicians are interested in general, is to identify some very particular or structured scenario of singularity. Like we look at with some certain physical constraints, like how you can develop such scenarios. So in particular, it happens naturally that we look for self-similar blowup. So here you can think of this f of t of x as a temporal and spatial rescaling of a profile function capital F. Now your capital F here is independent of time. So a very naive but canonical example you can think of is that your capital F is the standard Gaussian, and your small f is a family of rescale Gaussians tending to a Dirac, and the speed at how it's rescaling that basically relates to the blowup rate CF and CL here. So again, a lot of the equations exist with such some similar blowup. In particular, in the case of Euler equation in the presence of boundary, so not on the whole space, this Tom and his former student Guo Luo provided numerical evidence for self-similar blowup, which has since inspired a lot of very groundbreaking awards in mathematical fluids, including the work of Yindi, Chen Heng, among others. And finally, like a few years ago, with his former PhD student Jia Chen, Tom and Jia rigorously established self-similar blowup of Euler. But to go beyond the boundary, it can be also really challenging. And again, this rigorous proof is a computer-assisted proof. So to study beyond, we first study some modified one-dimensional models. But the punchline is that the original only Navier-Stokes, if you assume some regularity, like some constraints, then it's demonstrated both rigorously and numerically that it will not have self-similar singularity. So how to propose good answers for such singularity and how to compute are there like two very important problems. But let's zoom out a bit to discuss conceptually, how do we compute? And even with the computation, how do we make our proof rigorous? Because remember, it's a mathematical problem. You need to come up with an impeccable proof. So conceptually, it's actually quite simple the way I think of it. It's basically the punchline is that we transform the goal of such a priori estimate that you need to show the profile exists. And notice that in the profile formulation, it's already computing something nice. It's not computing something singular. And with the numerics, it sort of help us to translate that task into a posteriori type estimate, meaning that we have some approximate profile and we just have to analyze its stability. To be precise, there's basically two steps. The first step is numerically, you construct approximate profile with high precision in the residual. And the second step is to do some stability arguments, which basically is saying that there exists a true profile close to the approximate profile. And this is the hardest part because it's mostly analytical. And to basically encapsulate this analysis, you have here an ODE on your energy, you have a linear stability, have some nonlinear terms, and you have a small residual. If your residual is sufficiently small, then you can close the estimate. And finally, to make that all rigorous, because you can think of the approximate profile consists of like a couple of thousand terms or tens of thousand terms. You need to, of basis functions, you need to prove all that rigorously. So you represent every floating point by this upper and lower bound of interval, and you do interval arithmetics. But conceptually, that's the high-level idea of transforming a priori estimate to a posteriori estimate. And I want to argue it comes quite naturally. But just to going back a bit to relate to our non-uniqueness work, is actually also something similar in nature. So previously, people have already linked non-uniqueness to the study of forward self-similar solutions with unstable eigenvalues. And what we end up doing is use a very sophisticated numerical procedure, use finite elements, but also spectral masses to make sure we find numerical candidates that are of high precision and that are verifiable. We spend a lot of efforts, for example, to construct precise divergence-free spectral basis. And then what we do this perturbative stability argument, and it's not immediate, that is a linear stable, so we need to massage the operators a bit into a stable coercive part and a compact part, and then do some finite rank approximation. So I, of course, omitted a detail, but then we're able to establish the theorem. So now I would zoom out a bit. So I've talked about how to combine numerics and proofs. So in the interest in the scope here, I will probably be highlighting some of the numerics that we've done and also the community people have done, and some of the thoughts that we have concerning like potential directions, future directions of how to advance the numerics. Because again, as I said, you can think of the analysis and numerics are sort of a divide and conquer step. And it's of you have to rely on a good numerical solution to be able to perform the analysis. So we can focus on that part. I will mention a little bit about some analysis towards the end. So again, just to motivate, why do we need numerics at all? It's because the intrinsic complexity of the equations, you don't have explicit approximate profile. And also, even if you do, as is shown by the pioneering work of Yongji, Qingyao, Harvey, and Tristan, 2023 published PRNL, it can be unstable for time marching. So machine learning and optimization sort of offers a natural perspective, alternative perspective for that, and also to think about, because you're inferring the blowup law as well. So it's sort of an inverse problem of flavor. So neural networks, machine learning offers a natural a way of doing it. So some of the works I've done actually more impact in collaboration with Ziming Liu, sort of motivated by symbolic search for singularity. We pioneered the Kolmogorov Arnold networks, and also in terms of just using the neural network to solve those PDEs by itself to advance scientific machine learning. In collaboration with Professor Anima's group, we improve on some of their neural operators paradigm and also how to make physical neural network with higher precision. So again, it's not the key scope today, but just a quick encapsulate of our Akan work. We took inspiration from the Kolmogorov-Arnold representation theorem, and we parameterized the activation function by basically encourage them to be learnable with via the learning of their different coefficients. And so it's really inherits both the internal basis function approach, because we are learning 1D functions, but also inherit a connectionism of this neural network, and they make it interpretable and sometimes have a better scaling loss. And of course, we have a lot of follow-up works on studying kinds as well. And then, so I will talk a little bit about, so precisely, of course, Kant's was a symbolic approach on the architecture, but what other stuff can we use to drive the neural networks in the context of solving PDEs to higher precision? So I've talked about architectures, some other aspects that I think and what the community have looked at, which we think are of very interest, is that first, it's important to enforce some hard constraints on both your physical inductive bias, like including the parities of your solution, the far field vanishing condition, and the non-generated condition, etc. And also, it's important to build on, like, to look for other optimizers. So in our particular paper, we use still off the shelf, the self-scaled BFGS is a second order method because remember, we want to drive to high precision. So some stochastic or like base methods like Adam might not be ideal if you use a moderate batch size. So it's important to use some sort of a deterministic optimizer, but also the fully second order optimizer can make it challenging to scale up. So are there some like other alternatives like that reach in some sense a Pareto frontier in terms of scaling and accuracy? So we can explore some of our variants of a curvature informed optimizers like shampoo and soap, or even like more modern optimizers that taking into account of the matrix information of the coefficients like muon. So basically, and just even to zoom out to design and develop optimizers tailored for the need of the scientific machine learning, I think is of paramount importance, because if you just use some off-the-shelf optimizers that were designed for a vision or a language task, here PDE is a very distinct scope. For example, even in the forward problem, you oftentimes have derivatives in your loss function. So with backpropagation, that entails higher order calculation of derivatives, and it can make your optimization or problem formulation challenging. Okay, so beyond those, there's some other tricks like boosting, like learning ensemble of networks can also be helpful, but that's beyond the scope of this talk. So I'll just mention a bit, I'll dive a little bit into a detail about different aspects I've mentioned. So I'll mention about architectures, again, to iterate if you care about interpretability and expressivity, kinds can be a good alternative. Here is solving this challenge nonlinear PDEs. You might not care about interpretability. And there's some other interesting things we've looked at are like, for example, because you can imagine you can look for a family of solutions to different equations, different singularity. So neural operators might help in terms of your pre-training over a family of equations and fine-tuning on your single instance. And also you can borrow some, in particular, some of the upcoming or work we have with some people in the CV's group, where Brandon is a Caltech PhD. He was the lead in this project. Basically borrow some idea of hierarchical feature encoding inspired by the computer vision community, which can render the architecture be expressive. And I think it's quite good because even with the naive first order optimizer like Adam, we're able to reach 10 to the minus 8 of training accuracy, but of course on a very simple example of singularity in burgers. And then when we talk about inductive bias, like how do you physically encode your prior on the equation into your design of your machine learning algorithm. So I've talked about hard constraints, and also there's some other interesting work I've briefly mentioned, like how do you leverage the fact that you can learn a family of solutions, so in some sense, a continuation, a method. So if you, again, we care about solving a single instance for Navier-Stokes or Euler, which can be represented as some LU equals 0. But that equation, because we know it's quite challenging, we can sort of deform and play around modifying some terms. For example, we can suppress the terms that suppress singularity. So basically, I'll make the blowup terms more pronounced, where we empirically believe there's a stronger chance, and we've seen has a more robust way of blow up, and we can go from there in continuation to all the way of the true Euler or Stokes equation. or that's in terms of deforming the equation itself. You can also, instead of, as I said, instead of learning a single instance, singularity, you can also try to deform the right-hand side, so to learn a distribution of your solutions. And finally, as I briefly mentioned, we want to build a daily second-order optimizer that is also scalable. So one of the works we submitted to ICML this year is we improve the SOAP, first-order precondition optimizer that is curvature aware by some idea of a self-scaled preconditioning, as I mentioned before. And it seems to lie at a very good Pareto frontier, a very good trade-off between the accuracy of the method and also the training speed. And we applied, of course, to problems beyond singularity or beyond solving PDEs as well. And so that's some of the sort of a high-level overview of some of the numerical works that we've done. And so just to mention a little bit about the proofs. So basically, again, the idea is that you want to prove some sort of stability pertaining to your approximate profile. So here, the punchline we observed is that a stability can be achieved by a very careful rescaling of your time, because remember, to go from your physical equation to the profile equation, you have some rescaling of time. But if you choose that rescaling very carefully by enforcing some local orthogonality, then you can establish singularity, both in terms of as a numerical method to compute the singularity, but also to establish the singularity rigorously without using too much information of the approximate solution. So we developed that method across a wide range of equations, step by step, but like those are much simpler than the Navier-Stokes.
It's a quick question.
Yeah.
So how should I understand the function capital F? You say it's not time dependent, but actually rescale the spatial part of the equation. How should I understand the local orthogonality in terms of capital F?
Right. That's a great question, Yuanqi. So especially as you can see, there's a little bit of a nuance, a difference here in this answers. If you remember previously when we talked about self-similarity, right, that's also the title, beyond self-similarity, we don't have this subtle or log correction. Right. So here, imagine even just numerically, as time t tends to capital T, is very delicate because this log t is going to be small, like 1 over log t is going to be large, but still much smaller than the dominating factor. So how to identify, how to pick up this correction, it's very subtle. And going back to Yuanqi's question, how do you properly interpret your profile F is important. So you can think of this as a generalization. So here, we still, sort of the answers is still your physical variable is prescribed by some sort of a scaling of your profile. Again, the profile we think of it's almost constant, independent of time, or here it's like to the leading order is independent of time. But how we rescale it can be more general. Like it doesn't have to be this polynomial rescaling. Like here is just a perturbation, but we can also assume like more complicated way of rescaling things. But how to, and so by dynamic rescaling, what I mean is that if you work directly in the profile equation, which again is just a scaling of the original equation, but I did not write down. But if you work in that direction, you enforce stability in that direction, in that equation, then you can sort of automatically infer the law of this log correction at the same time. So we don't need to, that's what I said, we go beyond self-similarity, and we don't need to know the numerics or know the symptotics a priori, and our method can also be used to compute discover such a singular profile. Again, it's inspired by some some of the works in our group that in the self-similar regime, but it's great to go beyond that. And yeah, so basically it serves as a numerical discovery and the proof at the same time.
So I understand correctly, the lowercase f is some observable you're trying to observe across the flow, and you want to construct in a way that such that with this profile of scaling, it will blow up at capital T.
Right.
Yeah, because of like a T approach to capital T, you have this blow up structure.
Right.
And after you construct it, how do you know this construction is valid?
Oh yeah, that's a very good question. So as I said, basically you demonstrate this construction is valid by studying the profile equation. You basically see, oh, the profile solution, which is not going to be this precise f, but probably f plus some perturbation, but you see the perturbation is going to converge to a zero. Also in terms of how the time scaling relates to the asymptotics here, you're going to see, okay, to the linear order, the time rescaling are going to converge to this and this precisely.
But that's interesting. Is it like there's a finite set of functions that we know they're, well, maybe infinite, but like log, like 1 over 0, like log 0 or...
Yeah, that we don't know. Yeah, because as I said, in the past community, the self-similars, the primary thing that people care about, they're relatively like not that many works that has this. And then I was also aware that some numerical observation, there's some for nonlinear Schrodinger in a critical case, there can be a double log. But like, I don't know, like, yeah, so how can there be like other sort of scalings?
I see.
That's really challenging. But then the perspective we share is that if your intrinsic solution like don't have this a simple not a simple, but it doesn't have this sort of rescaling dictated by a single blob profile at all, then this can be drastically much more challenging because you can imagine it's a multiple, like a different profiles, each work at different scales. So that's a much more challenging answers, and both in terms of analysis and numerics, that can be much more challenging. So we're just exploring the most natural and physically makes sense scenario. Yeah. Oh, yeah, great questions. And then I finally mention the other perks of our method. We can, by this rescaling, we have a clear characterization of stability. We can also prove in scenarios like this kind of single equation, it's not unconditionally stable. So it actually has some unstable directions, but our method can characterize the unstable direction precisely. And then the whole punchline is that we don't use too much information on this approximate profile. And in the classical equation, we don't know the approximate, we don't know this capital F. We only know that theoretically we can do some analysis to show that such F exists. But then for more challenging cases like the Navier-Stokes, you don't know if such F exists at all. So you need to find it numerically and then do some perturbative analysis, as I was saying, I think earlier. So we call it, think of it as a sort of a non-intrusive way of using the information of this approximate profile, and this can make it potentially amenable to computer-assisted proofs for this much more challenging cases where you don't have an explicit profile, or like the Navier-Stokes. Yeah, so I have again some numerics, but we don't need to show. Okay, so finally this last slide, a perspective, to summing up on the different directions I've been pursuing in my PhD and how we can further push those directions. So I've briefly mentioned our idea of dynamic rescaling the time. So we can use it to find the singularity profile, but it can also go beyond, because think about if you want to solve a general time independent PDE, like general nonlinear elliptic PDE, sometimes you can add artificial time to solve it. But what we argue is that the naive way of adding artificial time and hoping to converge to steady state is not the best way. You can cleverly rescale the time to make the convergence much more stable and faster. And secondly, we talk about self-similar singularity. We talk about singularity with log correction, but how to go beyond that even further, how to study that with the singularity with multiple scales, like maybe not infinitely many multiple, but like a few multiple scale or traveling wave type. We have some preliminary study on that as well. And then to zoom out a bit down the non-uniqueness, our paradigm can be applied for other equations, this computer system proof. And then our architecture kinds, of course, can be applied for symbolic discovery and AF sense at large, but also in terms of just for advancing scientific machine learning, of computing PDE with high precision. I think we can study further some optimizer and theoretical aspects of machine learning to help us build such tools in a guided, informed way. And finally, I think maybe the last perspective is that right now it's constrained by the compute budget, constrained by the nature of academia or research. A lot of the, even in terms of high precision computation, our computation budget is still modest. So how to scale those up? And actually in PINs, like using neural networks, so PDEs, the scientific machine learning, I think it's a very hot topic in academia, but from what I understand, there's if you talk to experts in those real simulation companies, they still prefer traditional methods because they're more faithful, they're like better designed tailored to their need, to their like domain need, like how to design a bridge, how to extract oil. So like, how do you scale up those neural network based methods? That's of interest, because when I talk to people in academia, they just don't scale up. And they told me scaling architecture up is not beneficial, which I think should not be true. And it's quite counterintuitive to our common trend in AI in general, the impressive power of scaling laws. So like how to scale them up, like scaling up in which aspect, just the architecture or training time or sample size. I think how the way you sample it, that's going to be very interesting. And finally, if you scale this up and use some insights then this can help us better understand how it really compares to this traditional methods, especially in this high precision regime, because we know neural network-based methods are like much more versatile and can easily adapted for other equations. But again, the need is to touch high precision. I think a very few works in the community have pushed towards that direction, and I think that's
I'm actually curious about this scaling because you talk a lot about people try different optimizers, like a second order or more modern optimizers, or but by the end of the day, so is it like we are solving an existence problem? Like as long as we be able to find it, like because tuning optimizer sometimes feels like, oh, I mean, we overfit the problem or so on, but it's not a problem here because you're just showing the existence of the problem.
Exactly.
But would that be an issue like, for example, like if you have enough data? I'm not sure. Like you can fit anything with neural network.
That's a great point you mentioned. So I didn't talk in detail because I mentioned the nature of the scientific machine learning. So in PDE settings quite different from traditional machine learning like CV or NLP. Yeah. So precisely, for example, you touch upon the notion of overfitting. So what do we mean by overfitting here? Overfitting here is basically because here, imagine you don't have in some sense, it's unsupervised learning. You don't have a ground truth. Your loss function is governed by your sample of collocation point where you evaluate the PDE loss. So here the overfitting, I think, is in this sense, like how many points you sample. So at each step, of course, you can only sample finitely many points. Well, the hope is, okay, if you train for long enough and if you resample at each epoch, does it entail that it's able to generalize across the whole domain? The consensus and intuition is a yes. But I think how to prove it, that's another thing, but how to have a better intuitive understanding. The way one can draw analogy is actually from a discussion with a friend in the department. We actually quite like this analogy. Is think about comparing to traditional methods. Traditional methods, you have almost at each step you're doing a matrix inversion. So you have think about the equation in some discretized space. The trial and test space is always the same, or at least the same dimension. So if you want to scale up, then you need to scale up the space, and each time the cost is gonna scale like into the cube because you do some matrix inversion. Whereas here, you can scale up your architecture, and you scale up in some sense the test and trial space are completely different. The trial space is the space of functions your architecture can span, which because of the compositionality, the nonlinearity can be huge. The test space is the sample points of your sample, and you can think of at each epoch you're sampling a modest number of points. But if you train long enough, you're able to generalize. So in some sense, you have a very powerful generator, and you have an ensemble of different modest discriminators. Is that able to result in a very good generative adversarial network? If you think about that analogy, is that going to be able to generate a very faithful candidate in the end? The hope is a yes, but for example, even just scaling architecture, like how exactly do we scale, or do we just use a residual connection, and then, or do we use transformer? Or I think that's interesting.
I have a question, maybe philosophical, is that could we reframe the problem originally just like finding a function f, but now it's like capital F, but now it's like give a form of self-similarity. And now I only have a fixed way of doing Monte Carlo samples. But then could we just squeeze in those singularity or those messy, not generalized points into those regions, right? So I mean, like it's kind of like we trade one position to the other discretization via Monte Carlo simulation. Could that be possible? Because like maybe for arbitrary f, you can also minimize to a decent precision by just playing with the Monte Carlo samples you use. Like you do a maybe uniform finite gradient.
But the hope here is that you can, by allowing for a more general representation, you can look for more general similarities. Yeah, I guess that's possible. But then I always have the mental fear of if you are computing something infinite, then it's not ideal because neural networks sometimes you want to output to also be normalized in some sense. So my personal stake is I would still go treat these things separately, like a good answers, and then working that answers to find for something nice. But of course, you can do adaptive sampling for that. Mm-hmm. But I wouldn't directly try to simulate something infinite. That's my take.
Yeah. No. All right. Let's thank Yixuan for a great talk. We also have a lot of online audience that because this time doesn't work for Europe at all. So it's recorded, but
cool. Yeah. Because you have a branch in Europe.
Well, that's true, but we also open it all. It's it's very Yearly we have I think in the spring we have around 30 people, for each talk, and in the summer we have 50, 60 because there are more people here. Yeah. All right. So if you have any question, feel free to ask. But I have another question. I guess people might be curious as well. So what's the progress of so far towards this prize? So you showed in 1934 or something, people showed the existence.
No, that's the people construct so that's pertaining to the weak solution and non-uniqueness. So that's a different concept. But the strong solution, the singularity project is still concerning the question by itself is still concerning the strong classical solution, and people know it exists for short time. That's I forgot. Maybe also in the 30s or even earlier, but almost 100 years ago. But whether it's gonna develop singularity in a finite time, I think there's a lot of debates over the past century or something.
But the breakthrough by Junjie is a bit Junjie.
Oh, but
Like
Jiajie.
Jiajie in 2022. Could you interpret what was that breakthrough?
Right. So that breakthrough was, again, first, there's no viscosity, so it's all equation. Second is in the presence of a boundary. So boundary here plays an important effect in the development of singularities.
I see. So in that regime is solved.
Yeah.
In finite time, there is just a strong solution for the singularity.
Yes.
Okay, but now people want to understand what if without boundary
And with a viscosity.
with viscosity. Well, actually, I have some question about that because I study most of at molecular level. So we also see Navier-Stokes variable is just like continuity equation of some form.
Yeah.
We also study like Fock-Planck with viscosity. Like in our scenario, usually the viscosity helps.
Yeah.
Like why here it becomes even harder, like or would you say it's harder?
No, because the intuition is right, because normally viscosity helps stability, all right? So here, because we're studying singularities, sort of this viscosity is gonna suppress singularity.
Oh, it's even harder to find.
Yeah, yeah, so I guess the common consensus is probably, again, I'm just I'm just blindly guessing. I'm just speculating here, but for Euler singularity, it's even on the whole space, it's much more realistic.
Okay,
let's
want to tackle. And then would people say the prize is solved if people can solve that?
I don't think so. But it's going to be amazing results. No, but that's another statement of
I see.
Problem per se, because it's a really Navier-Stokes. Yeah.
I have a last quick question about this traveling wave. Well, I've heard about traveling waves in in fluid and in neuroscience. I think people use it. Like, could you give a little bit of intuition? Like, what does the self-similarity different from like things across multiple scale?
Yeah, that's a good question. So, for example, this traveling wave simple example, you can think of in the self-similarity here, the center of singularity. Of course, you can, because there's some translation invariance. Mm-hmm. But in some sense, after this, you see this sense, the singularity happens at the origin. So in some sense, this when the physical variable, because this x are divided by something, so yeah, x has to be a small for it to be a meaningful. But for traveling wave, you can think of the center of singularity is also a traveling. So it doesn't stay at its origin, and the travel could be traveling at a different speed compared to the.
Basically, you have some x
intrinsic
on x.
X minus some traveling a center. Yeah, so think about that. That could be already consisting of one different scale, or what if it's like two solitons interacting, so they can.
If you do try on those, would it be easier to solve, like to find the singularity?
Yeah, of course, because it's a more general answers, but then the numerical assimilation would be much harder. And because right now, especially with machine learning methods, how do you balance all of the different lost terms? It's already, because you have a handful of equations, handful of constraints. If you have more variables, then you have more constraints. How do you balance them in a realistic way? It's going to be challenging.
You have some questions? Okay, great. Thanks for coming. By the way, thank you everyone.
Thanks, folks.
Yeah, I know Yixuan is going to airport soon, so thank you everyone. And we'll post the recording maybe tomorrow.
Thanks.
Thank you guys. Bye.